Welcome to Mathematics. Today we'll be solving the Pearson Edexcel IAL January 2023 paper of Physics Unit 1. In the first question, we have to find which of the following is a scalar quantity. Displacement is a vector quantity. It has a direction. Moment of force has also, we also need to have a direction. So for this is clockwise and this is anti-clockwise. So the direction matters over here. So moment of force is also vector. Power is energy per unit time. Energy is a scalar quantity. It doesn't depend on direction. So power also doesn't depend on direction. So it must be power. If we look at weight, our weight is downwards towards the earth. So if this is me, this is my weight towards the earth center. So we have a direction towards the earth center. Now in question 2, we have to find which of the following describes gravitational field strength. We know that W equals to mg. We find this is the gravitational field strength. So if I make g the subject here, we get W by m. So we see that g is equal to W by m, or gravitational field strength is weight per unit mass. So A is the answer. In question 3, we are told that an object of mass m is resting on top of a string or spring. So this is a spring and this is mass m. We are told the spring is compressed a further distance del x by a vertical force F. So when we apply the vertical force F, it goes downward, and then this force is removed and it returns to its original length. So this was the original length. This is the original length. Now we are also told that del x becomes 0 and the object has a vertical velocity or vertical speed of v when that happens. So we can use conservation of energy over here. When it decompresses, it moves upward. So the object will gain GPE, it will also gain KE, and it will lose its elastic potential energy. So the change in elastic potential energy will be half into F into del x. So half F del x. The change in GPE will be mg del x. The height gained is del x. And KE will be half mv square. Initial speed was 0, so this was basically half mv square minus 0 square. This is the change in KE. Now the change in EPE or the loss in EPE will provide the gain in GPE and KE. So half F del x will be equal to mg del x plus half mv square. So if we look over here, B will be our answer. Now in question 4, we are told that a student measures the time taken for a steel ball bearing to fall a measured distance and then uses these measurements to determine the acceleration due to gravity. We have to find which of the following conditions is needed to determine an accurate value for the acceleration due to gravity or acceleration due to free fall. Now if I drop a ball bearing, if it's falling with acceleration equal to g, it will gain speed very fast. So if you drop something heavy or dense, so anything but paper or tissue paper, stuff like that, so if you drop your books, copies or pens, it will fall really fast. So you cannot expect the airflow to be laminar over. Again, we want to find the acceleration over here. If it reaches the terminal velocity, at terminal velocity acceleration is 0. So we will not measure the acceleration due to gravity. We'll measure an average acceleration for the journey. So this will be wrong. We would want the opposite to happen over here. Since we want the acceleration to be close to g for the whole journey, we don't want it to decrease to 0 very fast. So if I wanted to conduct the experiment at my home, I'd drop my books, copies, pens or paper. I would not drop a loose piece of paper and expect to get a good value. Now in the third point, it's worded confusingly. We're told that the ball bearing should begin to fall before the timer is started. So if I am holding this ball over here, and the moment I drop it, I start the timer. This is the usual way to do it. If I do that, I can find the initial velocity to be 0. Since I'm just dropping it, I'm not throwing it down. I'm gently releasing my fingers and it will start to fall down and its initial velocity will be 0. However, if I don't do that, so if I drop the ball first and then start the timer, which they want us to do in the third option, we will not know the initial velocity. This will hamper my experiment. So D will be the answer. If air resistance and upthrust is non-negligible, this has a mass m, its weight is mg. So from here, acceleration, so F equals to ma, the force on this is mg. From here we find the acceleration will be equal to g. However, in this case, if upthrust and the air resistance were non-negligible, we'll have an upward force on it. So upthrust plus air resistance. So now the acceleration will be mg minus u minus air resistance is equal to mass times acceleration. Now I cannot assume that g will be equal to the acceleration in this case. So we want the upthrust and the air resistance to be negligible for g to be equal to a. Now for question 5, we have a racing car that's passing point P at 35 meter per second and point Q at 50 meter per second. We have 5 seconds passing between them. We are told that the acceleration is uniform between them, so we have a constant acceleration. So we can use the Soviet equations. We know the initial velocity, the final velocity, the time, and we need the value of s. We do not know a, so we'll use the formula without a. So this would be u plus v divided by 2 times t. For here, s will be equal to 35 plus 50 divided by 2 into 5.0. So C will be the answer. Now in question 6, we are told that a soap bubble is being blown by the wind and its free body force diagram is shown below. So U is the upthrust on it, W is the weight of the bubble, and P is the force of the wind. We have to find which following vector diagram shows the resultant force F. In all the cases, we have W minus U given. So we can just find the difference between W and U. So subtract this length from W. So we subtract that length. So we'll have this blue part as W minus U. So this part is W minus U and that is P. So we'll draw a head to tail diagram. So we have the tail over here and the head over here of the W minus U vector. Now we'll join the P vector at its tail. So this will be the P vector at the tail of it. The resultant force will be this, and the arrow will be from the initial. So we started from here, our end point is here, so the arrow will be from the start to the end. Now if you look at the vector diagrams, we'll find that B is the correct one. B is the one that matches with our one. So we have P over here, P over here, the resultant force F over here, the resultant force F over here, the direction of the arrow is correct as well, and W minus U is correct. Over here, the arrow of F is in the wrong direction. In this case, F and P are reversed in both C and D. So B is our correct answer. Now for question 7, we are given the displacement time graph for a ball being vertically thrown up in the air and caught a few seconds later. We have to find the acceleration time graph for this. Since it's a ball thrown upwards, for the whole journey its acceleration will be equal to minus g. Since it's initially thrown upwards, and if I look at it, the velocity is the gradient of the displacement time graph. If I look at the velocity, it's continuously decreasing, so the acceleration must be negative. If the acceleration was positive, the velocity would keep increasing and be like this. In this case, acceleration is positive, this is wrong. In this case, acceleration is changing, this is wrong. G is a constant value, G doesn't change, so this will be a horizontal line and it will be negative, so B is the answer again. Now for question 8, we are told a motor that lifts a mass of 50,000 kg through a vertical height of 25 meters and has a power output of 700 kilowatt. We have to find the time it takes. So the energy required over here is 50,000 into 9.81 into 25, so GPE. Now we know that power divided by power into time is energy or work done. So we know the power is 700 kilowatts, so 700 into 10 cube, or basically 700,000 times t. The time taken will be 50,000 times 9.81 times 25. If I divide 700,000 from both sides, I'll get 50,000 into 9.81 into 25 divided by 700,000. So B is our answer again. Now in question 9, we have an experiment about the Young modulus of copper. We are told that the student adds known masses to a copper wire and measures the corresponding extensions. So the student wants to find the Young modulus of copper. From here he gets the value of the force, because he is adding known masses. The force will be mg, so he gets the force over here and he gets the extension over here as well. Now to find Young modulus, he needs to find the stress and the strain. Now stress over here will be force per area, so I need the area of the wire. To find the area of the wire, I need the diameter of the wire or the radius of the wire. So this will be pi d square by 4 or pi r square. And for strain, I'll have to find del x by x, where x is the original length. So I need the original length and I need either the radius or the diameter or straight up the area. So any three of them and the original length. In this we don't find the original length, in this we don't find the original length. Oh, we are told that they have to measure it directly. If we are told that we have to measure it directly, it has to be diameter. We cannot cut the wire in half and then measure its radius directly. So if I have a wire, I cannot measure its radius directly. I have to measure the diameter and then divide it by 2 to find the radius. If I wanted to find the radius directly, I'd have to slice the wire in half and then measure it. So it would be diameter and original length of the wire. Option B again is the answer. Now for question 10, we are told two forces make a Newton's third law pair. Which of the following statements is true for these forces? So we have to remember the conditions of Newton's third law pair. So the conditions are, so these are the conditions. Firstly, they must act on different bodies. So if I want to find the Newton's third law pair force for my weight, so for my weight, a common misunderstanding is considering the normal contact force to be the Newton's third law pair. This won't be the Newton's third law pair for weight because it's acting on the same body. The normal contact force from the ground or floor and my weight are both acting on me. They must act on different bodies. So my weight is due to earth. So the earth's gravity makes me have a weight. So the Newton's third law pair force must be on earth. So if earth is giving me a force, I am also pulling earth with an equal force. So if I have a weight of 70 g, I'll pull the earth with an equal force of 70 g. So they're acting on different bodies. So one is acting on me, the other one is acting on earth. They have the same magnitude and opposite direction, and they're the same type of force. So the force that earth exerts on me is a gravitational force. The force that I exert on earth is also a gravitational force. So if I look at the conditions over here, it says that same body. This is wrong. For B, we are told that this is the same type of force. This is correct. And different bodies, this is also correct. So B is correct. If I explode the other options, we are told that different magnitudes. This is wrong. Different directions is right. We are told that it's the same type of force. This is right. But they don't have different magnitudes. Now moving to section B. For question 11, we have a question about projectile motion. This is a stone that was thrown from the edge of a cliff horizontally. So its initial vertical velocity is 0. The initial horizontal velocity is 3.8 meter per second and the initial height is 12 meter. And for this question, we have to find the horizontal distance from the bottom of the cliff to where the stone hits. So basically the range of the stone, the initial horizontal. For that, using the vertical motion at first, I have to find the flight time. For vertical motion, we know that the initial velocity is 0. As the initial velocity isn't upwards, I can take acceleration to be g. I can take the downward direction to be positive right over here, since the initial velocity was 0. If it was thrown upwards, then I'd have to take a equals to minus g. Now we know that the displacement will be 12. Since I'm taking the downward direction as positive, the downward 12 meter can be taken positive. I need to find the flight time t. I don't have v, so I'll use s equals to ut plus half at square. So s is 12, u is 0, so this will be half into 9.81 into t square. The flight time t will come out to be root over 12 by half into 9.81. I'll keep the exact form for the next part. Now using the horizontal motion, I'll have to find the range. Now the horizontal velocity is a constant 3.2, this was 3.8 meter per second, and the time is given over here, so 12 by half into 9.81. The displacement, since there is no acceleration horizontally, I can use s equals to vt over here. So s is vt, so the range s will be equal to 3.8 times root over 12 by half into 9.81. So we get a range of 5.94 meters. Now moving on to question 12. In part A, we are told that when the ball is falling at terminal velocity, the drag force is equal to weight minus upthrust. The density of the liquid was known, and the student used the balance and digital caliper to make measurements of the ball. So from the balance, he found the mass and the weight, and from the digital caliper, he found the diameter. Now we have to describe how the student could use her measurements to calculate a value for the drag force. The drag force is equal to the weight minus the upthrust. So firstly, we measure the mass with the balance and then multiply it with g to find the weight. So we found the weight of the ball. Now I have to find the upthrust. The upthrust will be equal to rho v g, Rho is the density of air over here. Sorry, it was falling in a liquid. The density of the liquid is known. So this density is known. The volume of the ball will be 4 by 3 pi r cube. Instead of r, I can write d by 2 as well. So this is the volume of the sphere or the metal ball, and the value of g is also known. So from that I can find the volume of the ball, and from that I can find the upthrust. So if I structure my answer, I'll begin by writing how I calculate g, and then measure the diameter to find the volume, and then how I use the volume to find the upthrust, and then finally, as I have the weight and upthrust, I calculate the value of the drag force. So this is the first line where we talk about the mass and weight. Now the second line mentions about how the diameter d of the ball is measured using a digital caliper, and from that the volume of the ball is found using this formula. It's not necessary to write down the formula, but it's always safer to do so. And finally we finish by talking about how the upthrust will be equal to the weight of liquid displaced. So basically the definition of upthrust, and then how we can find that by multiplying the volume with the density of the liquid rho and the value of g. Because we know that upthrust equals to rho vg, we have to multiply the density and g with volume. Now for part B, we have a calculation. We are given the terminal velocity, the radius and the drag force. We are also told that the flow was laminar. We have to find the viscosity. Here we have to use Stokes law. So the Stokes equation is F equals to 6 pi eta RV. This is the viscosity. F is the drag force, so this is 1.1 into 10 to the power minus 2. This is equal to 6 pi into the viscosity, which is what we want to find, the radius of the ball, which is 0.5 into 10 to the power minus 2, times the terminal velocity, which is 5.4 into 10 to the power minus 4. From here I can make eta the subject. I'll get 1.1 into 10 to the power minus 2 divided by 6 pi into 0.5 into 10 to the power minus 2 into 5.4 into 10 to the power minus 4. The value of eta comes out to be 216.1, so 216 Pascal second. This is the unit of viscosity. So 216 Pascal second. We can figure out the unit from this as well. So we have force divided by a radius, so a length. So if I write the units down, newtons divided by meters into meter per second. So I have Newton divided by meter square into s to the power minus 1. If I take the s up, we'll have Newton second per meter square. Now we know that Newton per meter square is Pascal, since it's force per area. So from that we get Pascal second. Now in question 13, we are told that a builder is making a path using uniform rectangular stones, and the stone is resting horizontally on a step held in equilibrium by the builder's foot. So we have to state what is meant by equilibrium. Now if the builder let go of his feet over here, the moment would cause the stone to move clockwise. In this case, since we are given 2 marks, one will be about the upward force and downward force being equal, and the other will be the clockwise moment and anti-clockwise moment being equal. So we have 0 resultant force and 0 turning moment. So this is our structure, and this is how we answered this question. Now for part 2, we have to state what is meant by the center of gravity. So we have to just write down the definition of center of gravity, which we learned to be the point through which the weight of an object can be considered to act. So this is how we write the answer. Now moving on to part B, we are told the builder applies a minimum force P that will keep the stone in equilibrium. The position and direction of P is shown. Now we have to complete it with the other forces involved. So from here we'll have the weight of the step. So this is weight. We'll have another force. If we look over here, we have two downward forces but no upward forces. There must be upward force. The upward force will be from the normal contact. So from this point there will be a normal contact force on the stone. So somewhere along here from the ground upwards, this will be the force from the step. Now in part 2 we are given that the weight of the stone is 415 Newton, its length is 0.9 and this hanging length is 0.5 meters. We have to find the magnitude of P. P is the force provided by the man's feet over here. So we'll have clockwise moment equals to anti-clockwise moment. If we go back, we know that this is a uniform rectangular stone. So its center of gravity will be exactly halfway through. So this will be 0.45. Since we don't know the upward force, we'll consider the moments about that point. So we don't know this upward force or the normal reaction force provided by the step. So we'll take the moment about that point. Now about that point, we have this length. This is, since the hole is 0.9 and this is 0.5, this will be 0.9 minus 0.5, which will be 0.40 meters. And this length over here will be 0.50 minus 0.45, since this length over here is 0.45, we'll get a value of 0.05. So 0.05 times the weight of the stone, which is 415 newtons, will be equal to P into 0.40. The value of P will come out to be 51.9 newtons. Now for question 14, we are told about a metal cylindrical rod where we are applying compressive force. In part A, we have to state the definition of elastic deformation. We have to remember elastic means that the object returns to its original shape. Plastic means, so when it's plastic deformation, it doesn't return to its original size, and when it's elastic, it does return to its original size and shape. So this is how we define elastic deformation. Now we are given a graph of compressive stress against strain, and we have to show the Young's modulus. Young's modulus is a strain divided by stress divided by strain. So basically the gradient of this graph. If I take two suitable points, so I can take one over here, another one at origin. This point has a x value of, find that. Each 10 box is 0.5, so one box is 0.05. This is 1.55, 1.6, 1.65, 1.7, 1.75, 1.8, 1.85, 1.90. And for the y value, we have 4. So the gradient or the Young's modulus, which is equal to the gradient, will be y2 minus y1 divided by x2 minus x1. Here x2 comma y2 is 1.90 comma 4.0. x1 y1 is origin, so we have 4.0 divided by 1.90 minus 0 minus 0, basically 4 divided by 1.9. so the Young's modulus is 2.11 Pascal. We have to consider the units. The stress is given in 10 to the power 8, strain is given in 10 to the power minus 3, 10 to the power 8 and 10 to the power minus 3. If we consider that, we'll get 2.11 into 10 to the power 11 Pascal, which is close to 2 into 10 to the power 11. Now we are told that the metal part must not compress more than 0.6 millimeter when a force of 9.5 into 10 to the power 5 Newton is applied. We have to find if this metal is suitable for the part. We are given the cross-sectional area and the length. We have to find the compression. The Young's modulus will remain the same, so 2.11 into 10 to the power 11. This will be equal to the stress divided by the strain. The stress is force divided by area. The force is given 9.5 into 10 to the power 5. The area is 4.8 into 10 to the power minus 3. Over here we'll have the extension and the original length 0.84. We have to find the extension. The extension, we'll find this in millimeters. So whatever we find in meters, we multiply 10 cube with it. We'll have 2.11 into 10 to the power 11, which is equal to 9.5 into 10 to the power 5 times 0.84 divided by 4.8 into 10 to the power minus 3 del x. So del x is 9.5 into 10 to the power 5 into 0.84 divided by 4.8 into 10 to the power minus 3 into 2.11 into 10 to the power 11. The extension comes out to be 7.88 into 10 to the power minus 4 meters. So if I multiply into 10 cube over here, we'll get it in millimeters. So in millimeters we get 0.788. This is bigger than 0.6 millimeters. So the metal part this metal is not suitable. So the metal we were talking about is not suitable for doing this job. So therefore the metal is not suitable for this. Now moving on to question 15. We are told about a gymnast who bounces on a trampoline, and that for a part of each bounce the gymnast is in contact with the trampoline, and for the rest she is in the air. We are told the maximum upward acceleration is 14.2 meter per second square from the trampoline. We have to find the maximum upward force. We know that force is equals to mass into acceleration. Now we have to resolve the forces on the gymnast. On the gymnast we have a downward weight. So the gymnast's weight, which is 58 g. The upward force is the force from the trampoline, or the reaction force. And the upward acceleration is 14.2 meter per second. So the unbalanced force in this case is R minus 58g. This is equals to 58 times the acceleration. So we have unbalanced upward force equals to mass into acceleration. From here we'll find the value of R. This will be 58 times A. The value of A is also given to be 14.2. So we get a value of R. This would be, the value of R comes out to be 1390 newtons. The maximum upward force is 1390 newtons. Now moving to part B, we are given a spring at an angle of 14 degree. And the vertical components of this tension provide the upward force. We are given that the vertical component of the tension in one spring is 68 newtons and an horizontal angle of 14 degree. We have to find the tension in the spring. So the horizontal component or the vertical component is 68 newtons. From here we have to find the hypotenuse over here. So we know that this is 68. We have to find the hypotenuse or the actual tension. If I write sine 14 degree over here, we'll get opposite by hypotenuse, which will be 68 divided by the total tension. So T will be 68 divided by sine 14 degrees. So the value of T will be, the tension comes out to be 281.1, so 281 Newton. This is close to 300 Newton. This is 300 Newton in 1 SF. Now we are also given the extension of the spring. We have to find the stiffness. We know that the force is equal to K del X, where K is the stiffness. K will be F divided by del X. The force is 281 Newton from what we found before, and the extension is 4.6 into 10 to the power minus 2. So the value of K will come out to be 6.11 into 10 cube. The unit will be Newton per meter. This is the force, this is the extension. 6.11 into 10 cube Newton per meter. This is the stiffness. Now we have our 6 marker over here. We are told that the vertical acceleration of the gymnast varies while she is in contact with the trampoline. We have to explain how the forces on the gymnast affect the vertical acceleration while she is in contact with the trampoline. We have to identify the forces and direction of the forces on the gymnast. So we have a trampoline over here and the gymnast falls on it. After falling on it, the gymnast will keep on moving downward. When she moves downward, she stretches the trampoline more. So the normal contact force from the trampoline upwards will increase as she moves downward, with the normal contact force being maximum when the trampoline is at its lowest point or the gymnast is at her lowest point. The resultant force on the gymnast will be the difference between the normal contact force upwards and her weight downwards. The normal contact force will be greater than the weight, which causes a net upward acceleration. So when she's falling, she'll slow down and then start moving upwards. So if I structure this, so we begin by talking about the direction of the weight and the normal contact force. Then we move on to how the normal contact force changes when the gymnast is moving. So when the gymnast lands, just after she lands, the initial contact force is almost zero, and then she begins falling through the trampoline, causing the normal contact force to increase until its maximum at the bottom. So when the trampoline is like this at its minimum, this is when the normal contact force on the gymnast is maximum. We talk about that as well. So we talk about how the gymnast moving downward causes the normal contact force to increase until its maximum at the bottom of the bounce. Then we'll talk about how resultant force is the difference between the weight and normal contact force, and how the normal contact force is greater than the weight, so the acceleration is upwards. So we continue further with the answer. So we talk about how the resultant force is the difference between weight and normal contact, and when the normal contact is greater than the weight, the acceleration will be upwards. Now moving on to the next question. We have a spaceship over here that is used to take astronauts and equipment to the International Space Station. We have an orbital module, a descent module, and service module. Now the astronauts return to Earth in the descent module, and before entering the Earth's atmosphere, we're told that the modules separate. So we have the orbital module O, the service module S. So the orbital module and service module move away. So both of them move away from the descent module. We have to find the velocity v of the descent module after separation. So we can take this arrow to be in any direction. The final velocity of d, we can take this right or left. If our assumption is wrong, the value will come out to be negative, so we just have to flip the sign of the arrow then. Now taking it like this, the initial momentum will be 0 since they were together, so this is a case of explosion. So for O we have minus 1350 into 0.82, plus for D we have 2950V, plus for S we have 2100 into 0.58. This will be equal to 0. From here, if I want to find V will be 1350 into 0.82 minus 2100 into 0.58. The value of V for us will be minus 111 meter per second. So the arrow's direction was wrong. This will be 111 meter per second leftwards. So the magnitude is 111 meter per second and the direction is to the left. Now for question part B, we are told that the velocity of the descent module can be changed using a rocket motor. The rocket motor ejects hot gases at high velocity. Now we have to explain why the velocity of the descent module changes when the rocket motor is used using Newton's laws of motion. So we have a rocket motor. From here we have hot gases ejecting at high velocities. So there is the rocket exerts a leftward force on these gases. So by Newton's third law, the gas will exert a rightward force on the rocket. This will cause the rocket to accelerate by using Newton's second law, which states that F is equal to ma. And from that we know that this will accelerate, and if it accelerates, its velocity will change. So we talk about how the rocket motor exerts a force on the gas, and by Newton's third law, the gas will exert an equal and opposite force on the rocket motor. Due to this, there will be an unbalanced force on the rocket motor. So if we're talking about the descent module only, we have an unbalanced force on it, and hence according to Newton's second law, this will cause the descent module to accelerate. Now moving on to this part. So part B2, we are given the change in velocity is 0.58 meter per second with a time of 5 seconds, and we are given the mass of the module. We have to find the average force. From this we can from the change in velocity and time, we can find acceleration. Acceleration is the rate of change of velocity, so change in velocity per time. The change is 0.58, the time is 5 seconds. The acceleration is 0.58 by 5. We also know the mass, which is 2950. From there we can find the acceleration. The acceleration will come out to 342.2 newtons, so 342 newtons. Now we have a game called High Striker, where a person hits the button with a hammer, which causes the cylinder, so this cylinder, to move upwards towards the bell. If you hit it hard enough, it will hit the bell and start ringing it. In question A, we are told that the kinetic energy of the hammerhead as it hits the button is greater than the change in GPE of the hammerhead. So it's saying that when we drop this hammerhead on this button, the change in or the kinetic energy at the final point is more than the change in GPE we had over here. This is due to the player or us applying a force on it. So with our hand we are applying a downward force on it, so we are working on it, so we have an additional work done downwards. This will also contribute to the final kinetic energy. So when we are writing our answer, we first talk about the person applying a downward force on the hammer, and then we talk about how this is causing work done. This work done is the additional energy. This work done is also converted into kinetic energy, so additional energy is transferred to kinetic energy. Now moving on to the next question, or part B. We are told that the hammer is initially at rest at its highest point. As the person moves down the hammer, the average resultant force on the hammer is 58 Newton. So this is the force from the person's hand and its weight combined. We are told that the hammerhead moves up a distance of 1.2 meter before hitting the button, and that the cylinder must move 2.7 meters to hit the bell. The cylinder is this thing over here. The mass of the cylinder is given and the efficiency of energy transfer is given. So the input power or the input energy will be the change in GP of the hammer. So the mass of the hammer is, or we don't have to use mass, we have to use force into distance over here, since we know the force in the direction of motion and the displacement in that direction. So we'll simply use W equals to F into D, so 58 into 1.2. So the input energy is 69.6 joule. The efficiency is 4%. So 4.0 divided by 100 will be equal to the output by the input. So this is the output. We can write down this as E. We have 69.6 over here. The value of E will be 4 by 100 into 69.6, which is 2.784 joules. Now the cylinder must move 2.7 meter upwards and the mass is given. So it must gain GP to move upwards, and the GP must be provided by this energy. So the GP required for the bell to ring would be mgh. The mass is 0.15, then 9.81 for the gravitational field strength, and the height that it needs to move is 2.7 meters. So if I calculate this will come out to be 3.97 joules. This is less than the energy we have. So GPE required is more than the input energy or the output energy over here. This was the input energy. We are considering the output energy over here. So output energy, since we do not meet the requirement or the required energy, the cylinder won't hit the bell. Now moving on to part C, we are told that if the velocity of the hammerhead as it hits the button doubles, the height gained by the cylinder does not double. We have to explain why. Here if you notice, we are talking about the velocity of the hammer, not the kinetic energy. The height gain depends on the GPE, so we have mgh equals to half mv square. So the kinetic energy is converted to GPE. If we look at this, it's dependent on the square of the velocity. So if I double the velocity, if I put 2 over here, we'll have 4 square over here, or sorry, we have 2 square over here, which is 4. So the velocity, if it doubles, the height gain can even quadruple. So the kinetic energy is half mv square. So if I double the velocity, the kinetic energy will quadruple. So the cylinder can move 4 times the distance it moved before. Now moving on to the last question. We are told that an object of mass 35 kg fell from a boat to the seabed and reached terminal velocity as it fell. We have to show that the drag force was about 200 newtons. We have the volume and density of seawater. If I draw a free body force diagram, it's moving downward, so the drag, Stokes drag, must be upward. The thrust is also upward. The weight is downward. So we have W equals to U plus D. If I make D the subject, we have D equals to W minus U. So the drag will be equal to the weight. So 35 times G is the weight minus U. The upthrust will be rho. So the density of the liquid, so density of seawater in this case, times the volume of the object times G. Here it would be 1.03 into 10 to the power 3 times 1.60 into 10 to the power minus 2 into 9.81. From here, if I calculate D, it will come out to 181.7, so 182 Newton. The weight is mg, this is rho vg. Now the drag force, we are told that the drag force D on the object obeys this formula over here. So K times V square. The value of K is given. V is the speed of the object. We have to find the terminal velocity. So at terminal velocity, the drag is 182 newtons. So 182 is equal to K, which is 2.2 times V square. So V terminal, this will be V terminal squared. So the terminal velocity will be 182 divided by 2.2, and we have to square root that. So the terminal velocity will come out to be 9.09 meter per second. In part A3, we have to give 2 reasons why Stokes' law could not be used to calculate the terminal velocity. So the conditions of the Stokes' law being applied is we are having a small spherical object and having laminar flow. So these are the conditions required to apply Stokes' law. So 2 reasons why we cannot use Stokes' law would be this conditions not being met. So the object might not be spherical, and the object might not have laminar flow. Sorry, not the object, the seawater might not have a laminar flow around the object. Flow might not be laminar is the second point. Now for part B, we are told that to lift heavy object from the seabed, a lift bag is used. A diver used compressed air from the cylinder to fill the lift bag. So the compressed air of his air tank He uses that to fill the lift bag with air. Now we are told that when released, the lift bag and object accelerates upward until they reach the maximum velocity. We have to explain why they reach the maximum velocity. In this case, we have an upwards terminal velocity. In this case, we don't call it a terminal velocity since it's moving upwards. So initially we have upthrust and a small weight in comparison. So the upthrust is much bigger than the weight. Then as it starts moving upwards, the drag force upwards increases. The drag force downwards. Now since it's moving upwards, the drag will be downwards. As the speed increases, the drag keeps increases until u becomes equal to w plus d. When that happens, the resultant force becomes 0 and the object stops accelerating. So we talk about how the drag force increases with velocity until it becomes until the weight plus drag becomes equal to the upthrust, and at that point resultant force is 0. So we talk about how increasing the drag forces. So we talk about how as the velocity increases, the drag force also increases, and this happens until the drag force and weight will be equal to the upthrust. So downward force equals to upward force. If that happens, the resultant force is 0, and since the resultant force is 0, the acceleration will be 0. The object won't accelerate anymore. That's it for this paper.